Hello everyone. I should have erased this, whatever, I'll erase it in a minute. So I've been told that the video of me is a little bit choppy, but the audio sounds okay. Is that good? Alright. I think I have things set up so I'm recording this locally on my computer. I think I have it set up properly now. But maybe it's causing it to be a little choppy. But hopefully that'll be okay because you can still hear me and you can see what I'm writing on the board. Maybe not like exactly in real time. But there will be a nice video of me that'll be like the whole screen instead of like me plus 3 students like the Teams recording was. The only downside, I guess, is that, or maybe it's an upside, I don't know. It's the thing about it is that like none of you will be in the video because it's being recorded on my computer before it gets sent out to Teams. So like if you ask a question, that won't get recorded in the video. So I'm going to try to remember to kind of like briefly restate. If someone asks a question, I'll like briefly restate it on the video, so that way if you watch the video later, you'll kind of know what was being talked about. But again, I very much encourage you to type stuff in the chat. It can be either questions for me or just like comments, jokes, whatever you want. You can use the chat however you want. If you do have a question, you can like raise your hand in Teams or just unmute yourself if you had something that you want to stop me and have a question. So today we're going to talk about BreadthFirst Search, which is kind of the first graph algorithm we're going to talk about, and it's incredibly important and versatile algorithm. And it has some nice theoretical properties. It's kind of a building block that we're going to use for a lot of other things later as well. So first, as kind of a quick review, you may remember going over this when you took data structures. It kind of depends on what was covered. But just like, how do we actually represent graphs in a program? So you all remembered what graphs are last time, went over some terminology. But if we wanted to write a program that's actually going to manipulate graphs, how do we represent it? And so typically we'll use something called an adjacency list. So representing graphs. So just as a quick example, like if I have this graph here, I don't know, we'll call this A, B, C, D. So if I have this graph, an adjacency list basically says for each vertex, what are the other vertices that are adjacent to it? And so we would have like, A, okay, so I wrote this as like A maps to like the set containing the vertices B and C. And B is going to map to A and C. C maps to A, B, and D. And then D would map to just C by itself. So this is called adjacency list representation. Or, I mean, it's called adjacency list if you think about having a list of vertices, but we often might use a set instead of a list because we don't actually care about the order necessarily, just like which vertices are there. So this would be something like, it's like a dictionary or a map from vertices and vertex to set of, I'm just going to say V for vertex. So this is kind of Java-esque notation, I guess, but it just means it's a map or dictionary, right? That the keys are vertices, and the values are associated with the vertices are, the set of vertices that are adjacent to each vertex. Okay, and this most of the time when we're talking about graph algorithms, we'll talk about this, we'll use this kind of representation. Because we most often want to say, we're at some vertex, let's look at all the vertices next to it, and this makes it very easy to look that up. Occasionally you may see like, a matrix, like where the rows and columns are both vertices, and you just, each cell is like, is there an edge between those vertices? We'll see that come up later in the semester, but usually we'll stick with this. And in the case that like the edges have weights on them, so sometimes you'll, like an edge will have a number or something associated with it. Then instead of just a set of vertices, you could have a set of like edge objects. And each edge object might store, the vertex on the other end of the edge plus a weight or some other information associated with the edge. So I'll just say, or set of edge. All right. Questions about that? Okay. So right, if you're using Python, you can literally use a dictionary. If you're using Java, you probably want to use like a hash map or something. Right, and in particular, using a hash table-based structure means that we can look things up or change something for a vertex in constant time. So, and that's, we'll kind of, when we analyze the running time of algorithms, we're going to be typically assuming that we can look up information about a particular vertex in constant time. That we're using some kind of hash table structure. All right, that's that. So. So we're going to look at something called the ST connectivity problem. Just kind of a fundamental question that we can, or a set of related fundamental questions we can ask about a graph. And we're going to see that BreadthFirst Search is the algorithm that is going to answer these questions for us. So for example, right, given vertices S and T in a graph, is there a path from S to T? Right, or put another way, in terms of the vocabulary you all learned in the day, right, are S and T connected? Does there exist some path where I can walk along edges from S and eventually get to T? Right, and this kind of question comes up all the time. So imagine like, you could think of a graph where the vertices are people and the edges are like connections in some social network, and you're like, I want to meet that other person. Does there exist a path from me to them where like I could kind of be introduced, along people that know each other? Or think about like, a graph where the vertices are locations around the floor of a warehouse, and you've got a robot that's at one position and wants to get to another position, and it's got to like plan out, like, is there a path for me to get from where I am now to where I want to be? And so then the other related question, in both of those scenarios I said, we probably don't just want any path. We probably would prefer to have a shorter path than a longer path, right? Like, I don't want to go through like 27 people to be introduced to someone. I want to find, what's the shortest chain of people to get me there. And likewise, the robot wants to save energy. It doesn't want to like go all the way around the long way. It wants to like find the most direct path. So a related question we can ask is, what is the length of the shortest path from S to T? Okay, and we can answer both these questions with BreadthFirst Search. Which from now on we're just going to abbreviate as BFS do chalk soon. All right, so what's the idea of breadth-first search? So here's the basic idea. So we've got some graph, we've got some starting vertex S, and we want to look through the graph, like starting from S, and go out layer by layer. So sort of, we say, okay, the first layer is, well, I'll just say that S is my kind of 0th layer, right? So this is layer 0. And then I say, okay, I can get from S to a few other vertices, in one step, right, by following a single edge. And I'm going to call all those vertices, that's my layer 1. And maybe, I don't know, maybe there was an edge like between some of those vertices, but I don't really care. I only care about, how quickly can I reach those vertices from S. And if I then say, okay, well, from any vertex in layer 1, are there any new vertices I can get to? So maybe there's something like this. Right, this would be my layer 2. Right, and so on. So I'll just keep. Right, at each step, I say, okay, let me take all the vertices in my current layer and go along one edge and see if there's any new things I can reach. And that'll be my next layer, and so on. Okay. Okay, does that make sense? Any questions about how that's going to work? All right, I'm going to get a new piece of chalk now. All right, so here's a few properties of breadth-first search. And these are the kind of things that hopefully each of these properties we're going to think about and be like, yes, that makes sense, I believe that, it seems obvious. But it's also the case that when you're doing something with breadth-first search, sometimes it's helpful to remind yourself of these properties, because even though they're kind of obvious once you think about them, figuring out when to apply them or when to use them may not be quite as obvious. Or the properties may not be as obvious when you're thinking about breadth-first search in some particular scenario, instead of thinking about it kind of generically. Okay? So, here's number 1. The shortest path from S to V. So S is my starting vertex. V is just any other vertex. So has length I. If and only if V is in layer I. Okay, so S itself is in layer 0, and it's the only vertex where you have a path of length 0 to get from S to itself. Right? Everything in layer 1 are all the things that I could reach from S by a single edge, a path of length 1. And then everything in layer 2, right, those are the things that I had to take 2 steps to get from S to those vertices, and so on. And if you think about it like, you're like, well, how about if there was something in layer 4, but it actually has a path of length 3, right? Could that happen? And it can't, right? Because if there was some path of length 3 to get there, then it would have showed up in layer 3. Because we're going to all the vertices that it's possible to get to in one step, and then all the vertices it's possible to get to from them, and then that path of length 3 would have made that vertex show up in layer 3. So to do a formal proof of that, you would do it by induction on the length, and you would just say, well, if this is true at one level, then the next level I include everything that it's possible to get to in one more step, and so that's still going to be true of that next level. We're not going to write out a formal proof, but I'll just say, you know, proof induction. Okay. Number 2, there exists a path from S to T if and only if T shows up in some layer of the breadth-first search. Okay. Again, maybe, hopefully that seems kind of obvious, right? If the first thing is true, you know, if there is a path from S to T, then it has some length. And so if there's a shortest path that has some length, then it has to show up in that, you know, the layer corresponding to that length. Another way to say this, right, even without thinking about length, it's just like if we start at S and we keep following all the edges we can, we're eventually going to get to everything we can possibly reach. And if there's something we didn't get to, then it's because there was no way to get there. There was no path, right? So we could have, you know, 2 completely separate, disconnected, or connected components. And if we start doing a breadth-first search from one, we'll get to everything in that component, and we will never get to anything in another component. Okay, here's another one. For each edge UV in E, the layer of U and V, the layers, I'll say the layers of U and V differ by at most 1. Okay, why is this? So another way to say this is, right, if I have an edge, 2 vertices that are connected by an edge, it's not possible that U would show up in layer 3, say, and then V would show up in layer 5. And when you say it that way, it's like, well, of course not, because if U shows up in layer 3, and there's an edge between them, then V is going to show up in the next layer, because we follow all the edges that we can to get the next layer. Now, they could show up in the same layer. That can happen, right? So in this example here, right, I had this edge here was connecting these vertices, but these 2 vertices are in the same layer. That can happen, but they can never be. They could be in the same layer, or they could be different by 1 layer, but they can never be any farther apart than that. Questions about any of these properties so far? Okay. So here's another way to think about what breadth-first search is doing. So I had this one picture I drew where, you know, I had the vertex in the middle, and then we were kind of like, the layers were kind of concentric circles going out. Another way we can think about drawing it, I can put the starting vertex S at the top, and we think of the breadth-first search as kind of making a tree. So each layer of the search is 1 more level in the tree. So this is, you know, layer 0. So I can also think of BFS as a tree, right? So then, you know, we follow some edges, and we get to layer 1, and then there might be some more edges here. Get to some vertices in layer 2, no, layer 3, and right, there can be other edges, right? Like again, maybe there was an edge here, and maybe there was an edge here, or maybe there could be an edge like here, right? So there's some in the picture I've drawn, the white edges are the edges that the breadth first search actually followed to get from each layer to the next. There could be some additional edges that I've drawn in green that can only ever go either between vertices at the same level or between vertices on adjacent levels. And it sort of, it makes the whole graph into a tree like this, or the connected part. And the way that we're gonna, and often it's helpful to actually store this tree explicitly. So if you just want to know, we had a question over here, if you just want to know, say, I'm trying to get from S to T, is it possible to get from S to T or not? Then you don't need to keep track of much, you just do the search, and if you ever see T, then you stop, and you're like, yes. And if you never see it, then, and you run out of things to look at, then you say no. But what if you actually want to know, like, I don't just want to know if it's possible, I want you to actually tell me a path. Like, how do you get from S to T? Well, then we want to store this tree. And the way we do it, and we're going to use this trick a lot, when we're searching in a graph and we want to store this tree, we don't bother storing. So one way you could think of doing it is, for each vertex, you store like the set of all its children in the tree. That's too much work. What we're going to do instead is just for each vertex, we're going to store its parent. Right? In a tree, every vertex has a single parent. And so we'll just store a ParentMap. And I will often use the Greek letter pi, which stands for parent, where pi of v is the parent of v in the tree. Okay, and each vertex just has one parent, except the root, which doesn't have a parent. And typically, like, you could just make the root kind of its own parent, or maybe put some special value in there so you know it's the root. Doesn't really matter, but just somehow you can tell when you've gotten to the root. And so, the way that you would find a path is you could do this search, and then, if you're trying to find a path from S to T, you would say, okay, let me look up the parent of T, and it would tell you, okay, that's this vertex. And then you look up the parent of that vertex, which gives you this one, and then you look up the parent of that one, and you're like, okay, I finally got back to S, and that gives you, the path in reverse order. So all you have to do, you do the breadth first search, and then you look up the parent and the grandparent and the great grandparent and so on of the thing you're trying to get to until you get back to your starting vertex. So Daniel asked a question, does this still work when S has more than 2 vertices connected to it? Yes, absolutely. So, I mean, it just looks, it would look like this. I don't know, it could be a bunch of things. So, good. That's a good question, though, because I'm not talking about binary trees. It's just a tree. A rooted tree, because we just talked about trees the other day, like a graph theory sense tree. This is a rooted tree, that each vertex can have any number of children. And that's part of why it would be annoying to store it that way, because we couldn't just have like a left and right. We'd have to have like a set of all the children. But we don't care, because we never care about being able to go down the tree. We only care about being able to start somewhere at the bottom and following a path up. That's why we can get away with just storing the parent of each vertex. And that's good enough. Cool. Good question. Other questions at this point? All right, so the next thing we're going to do is we're going to actually write down. So far we've talked about breadth first search kind of in a hand-wavy sort of way, where we said, well, this is kind of, in general, it works by going out layer by layer. But let's actually write down some pseudocode to make it a little more formal how the algorithm actually works. And so hopefully, I'm not going to actually write down like Java code or Python code or something, but hopefully when I write the pseudocode, it'll be at the level that you could take it and easily translate it into Python or Java or C++ or whatever. And I think I've mentioned that before, maybe not. Right, I'm not gonna, you're never gonna see me showing any code in a real language in class. Sometimes on, solutions to homeworks, I may say, well, I implemented this in Python, here's my code. But when there's a coding component on your homework, you're always free to use whatever language you want. And so actually on this week's homework, there will be some code you have to write, but you can use whatever language you're most comfortable with. You're welcome to use it. So, okay, so BreadthFirst Search is given as input a graph G. I should really say I'll say G, which is some vertices and some edges, right? And then it's also given a starting vertex S, which is in the set of vertices. So here's what we're going to do. The way we're going to keep track of the vertices, so as we go out layer by layer, we kind of have to keep track of what are the vertices that we have yet to process for the next layer. Now one way we could do that is by having a list of sets, and so the first thing in the list is layer 0, and the second thing in the list is layer 1 and layer 2. You can do that, but it turns out there's a cool trick we can use, which is we just use a queue. And when we use a queue, right, as we put vertices in the queue, we're always going to finish processing the vertices from the previous layer before we get to processing the ones from the next layer. And so we really are going layer by layer, but we don't bother keeping the layers separate, right? They're just all going to go in a queue, and we just know that they're going to kind of go in order by layer. So we'll initialize a queue. And we'll make our empty dictionary. Right, this is for our parent map. I'm also going to make, so I'll write that. So this is our parent map. This is another empty dictionary. I'm going to call this our level map. So the level map is going to keep track of, for each vertex, what level did it end up in? What layer did it end up in? Because sometimes we might like to know, once I do a BreadthFirst search, if I can look at a particular vertex and say, how far away was this one from S? And to answer that question, I can just look it up in the level map and say, oh, it had level 5, so that means the shortest path from S to that vertex was 5. Okay, so we're going to start by one thing that, well, let me say this. Let me write it first. So mark all vertices unvisited. So one thing that is, maybe I'll use this as an example. So in this picture here, right, so let's say we followed this edge and we saw this vertex in the next layer, but then later we processed this vertex and we followed this green edge. How did we know not to process this vertex a second time? And the answer is we have to keep track of which vertices we've seen so far and which ones we haven't seen, so that we don't end up processing a vertex multiple times. Okay, so that's what we're doing here. So we're going to start out by saying everything is unvisited. I haven't seen anything. And as we see them, we're going to mark them as visited, and then we'll also have a check somewhere that says, if this has already been visited, then forget about it. We don't need to worry about it. And we could do that by, having an array of booleans or some kind of, a dictionary that maps from vertices to booleans or something like that. Okay, so we're going to first start out by initializing S. So we're going to mark s as visited, and we're going to add s to the queue, and we're going to set okay, so this is, I put this all on one line because it would really be like 3 statements in any programming language, but it's all about kind of initializing our starting vertex s. So there's 3 things we have to do. We have to say, yeah, s has been visited. I don't want to, if I come back to s later, I don't want to redo anything. We're going to put it in our queue to start as the first vertex to process, and then it starts out, its level is 0, right? So then we're going to say while queue is not empty. Right, so this is the way we know, this is how we know when we're done. When the queue becomes empty, it means there's no vertices left to visit, and we've kind of looked at everything that we can, and then we can stop. So we're going to take a vertex, the next vertex out of the queue. I'm going to call it u. So this is like, I'll draw this little picture. So we're in, right, we're at some layer, and this is level like, layer I. This is the next vertex we want to look at, u, and we want to look at, some other potential things we can visit from u. So we want to look at all the neighbors of u. So for each edge u comma v adjacent to u, right? And here we see this is why it's nice to have the adjacency list representation, because for our vertex u, we can quickly look up and see what are the edges that are going out of u. Okay, so one thing that could happen, right, is that v, maybe we've already visited v. Maybe we've already seen v. In that case, we don't want to do anything, because we're pretty much done with that vertex. So I definitely want to have an if here that says if v is unvisited, okay? And I won't have an else because there's nothing I want to do in that case. So, and at this point I want to get ideas from you. So there's a few different things we're going to have to do to process v. So I'm now in the case where we've found a new vertex v that we have not seen before that we can get to from u. What should we do with it? Ideas?
Add it to the queue.
Add it to the queue? Good. Yeah, so add v to queue. Okay. Someone else? What's something else you think we should do?
Set the level and mark it as visited.
Set the level, right. Oh, and you said and mark it as visited?
Yeah.
Yeah, good. So definitely we should mark it as visited, because if we ever see it again, we don't want to process it again. So mark v visited. What should we set the level to?
One plus the level of s or the previous one.
Yeah. So right, the previous one is u. Yeah. So exactly, we can look up and see what the level of u is. It's already been set. So if it's in the queue, right, it's already been set. So we can just make the level of v one more than the level of u. Because if we haven't seen v before, and it's connected to u, like it couldn't have been in the same level as u, or else we would have already seen it. So we're going to set level of v to be level of u plus 1. Okay? And someone else, there's one more thing that we should do actually.
Remove u from the queue?
We already did that. Like, that was the first thing we did. We took the next thing out of the head of the queue, and that was how we got u. So, yes, we need to do that, but we did. The other thing is kind of optional, but it's something that we said we wanted to keep track of.
Add it to the parent.
Exactly, yeah. We made this parent map, and we haven't actually used it anywhere yet. So right, this is kind of what's keeping track of this tree for us. So we know kind of, because we want to remember, hey, yeah, I got to V, and the way I got there was from U, right? U was the parent of V in this search. So I'm going to set the parent of V to U. Okay, that's it. Good. Questions? So there's kind of a lot here, and some of it is optional. So in particular, the stuff about the parent map and the level map, we could leave that out if we don't need it, right? So for example, if all we care about is, can you get from S to T, then we could just kind of leave those things out and we don't need to keep track of them. It's more about, yeah, I guess then I should put at the end, like at the very end, I'll just say like return, it's like pi and level. It's kind of the information that we're getting out of doing the search. And we could use those to look up. We can use the parent map, right, to reconstruct for any vertex. That's the interesting thing about this, actually, right? I framed the questions in the first place in terms of trying to find a path from S to some particular T. But notice we don't take any particular T as an argument here. It just searches from S to everywhere. And once we've done that, right, any other vertex, we could look it up in the parent map and follow its parents until we get to S, and that would tell us the shortest path from S to that vertex. And the level map will tell us the level of any the length of the shortest path from S to anything. So this is called the, I'll just put this up here as kind of as an aside. This is the single source shortest path, SSSP problem. And BreadthFirst Search is one thing that solves that problem in the particular case of graphs that don't have weights on the edges. We'll talk about what you do with weights on the edges later. But, and there's also what if you want like shortest paths between any two vertices? Well, there's other things you can do. But this is just like if you have one starting vertex and you want to know the shortest path from that to anything else, you can do this. So yeah, if we don't need them, we could leave out the parent map and level. You can also kind of sometimes use a trick where you can kind of reuse the level map or the parent map to know whether something's been visited. Like if you initialize it to you initialize the levels to all -1, for example, then you know whether something's been visited or not based on whether its level is still -1. Then you don't really need a separate marking something as visited step. And if you want, right, you could also pass in a target vertex t if there's something in particular you're looking for, and then you could change this loop to stop as soon as you see t. You could stop early because you don't need to keep going at that point. So there's some different variants, but this is kind of like a good generic version that you'll be able to adapt to whatever situation. So how long does this take? So we might look at this and say, well, let's see. There's two nested loops. Here's a while loop and here's a for loop. So n squared. So that's actually wrong for two reasons. Number one, what is n? We often talk about n when we're talking about big O and big theta or whatever, but you have to actually know what n represents when you say something in terms of n. And with a graph, like there's the number of vertices and there's also the number of edges, and those both matter. And so when we talk about the running time of graph algorithms, we often will need to distinguish between the number of vertices and the number of edges. The other thing is that just because you have two loops doesn't mean that they, you have to think about how many times those loops execute. So, let's see if we can do this. So I claim, and this is a trick that we will often use. So this loop, how many times does this loop execute? This is the easy one. How many times does this while loop execute? In the worst case.
N times.
Yeah, and what is n?
Vertices.
Right. So the number of vertices, right? Because we only ever take each vertex out of the queue once, because once it's been put in the queue, we never put it in there again because we mark it as visited. And if if the whole graph is connected, right, then we're going to get to all the vertices eventually. So that's easy. So this loop is O of n. I'm not going to put n. I'm going to say O of v. So v just means the number of vertices. What about this loop though? How many times does this loop execute?
The number of edges.
Well, yeah, I mean so for a particular time this loop happens, it's only the number of edges connected to a particular vertex, right? And that could be very different for different vertices, right? So one time through this might execute a lot, and another time through it might execute, if there's only one edge, it'll execute just once or something. So my point is we cannot analyze this just by saying, oh, there's nested loops, so I'm just going to multiply this times this, and that's the answer, right? Because this executes different numbers of times, depending. But we can say this, right? How many times does this loop execute in total, over the entire algorithm? So I'm going to come to this loop multiple times, but if I add up all the executions of this loop, right? How many times is it going to execute? What was that? Did you say E or B? E, like the number of edges?
Vertex.
Wait.
I was thinking the number of vertex.
Vertex, right. Okay, vertices. Yeah, why?
Each edge is going to be connected to a vertex, and that's what we're really looking at is the vertex.
Yes, but you can have multiple edges connected to one vertex, right?
But we wouldn't count that second edge.
Well, we still do the loop though, even if this if doesn't, even if the if is false, right? That still counts as doing this loop one time, right? If you have a loop that goes a million times and then right inside the loop is an if that doesn't happen, I mean, you still have to do it a million times and check the if a million times, so that counts for something. So yeah, so one way to think about it is, right, each edge, I claim that each edge we look at twice, right? Once in each direction. So because we're looking at every vertex once, right? Every vertex we're going to look at all the edges going out of it. And so each edge we're going to look at twice, once in each direction. Like one time we look at this vertex and we look this way, and then another time we'll look at this vertex and look this way. So this executes, right, 2 times the number of edges, which is just O of E loops total. And I'm really underlining total because, again, I'm not going to multiply this by this because it's not like it happens this many times every time through this loop. We're just saying overall. So in the end, like, we actually don't care about this. I mean, that helped us analyze this, but since this is total, we can just, that's the answer. Like, that's how many times this whole thing will happen. Okay, so we only have a few minutes, but claim BFS can be implemented to run in theta v plus e time. And we only have a few minutes, so I'm just going to kind of wave my hands a little bit through this. So all this stuff of like initializing things, we assume that's going to be fast. Or maybe, you know, no, like these things are going to be fast. Marking everything as unvisited, like, depends on how we do it, but maybe we'll say that's going to take theta of v time. Like if we have to initialize an array with all the vertices and set everything to false, like maybe that'll take v time, right? This stuff all takes constant time, right? We're assuming however we represent it, visited and unvisited, we're going to be able to update it in constant time. Adding something to a queue, we're assuming that we can implement queue operations in constant time, which we can. Right, and we're also assuming that we can implement our dictionary operations in constant time, so we're using some kind of hash table based thing. So the point is, like, that's why I stated the claim as can be implemented to run in this time. It's not really, doesn't really make sense to say BFS takes this amount of time. It depends on how you implement it and what data structures you choose. Right, and then this whole thing goes around you know, E time. So right, this stuff takes like some constant time, maybe a theta of V time here. This whole loop goes around E times. And then the question is, how long does this stuff take? And I claim that all this stuff also takes constant time. Right, so all we're doing is we're adding stuff to a queue, marking something visited, setting some things in some dictionaries. And so each of those things is going to be constant time. There's like 4 of them, right? Doing 4 things that each take constant time is also constant time. And so we do a constant amount of work, you know, theta of E times. And so this takes theta of E, this takes theta of V, and so the total is going to be their sum, because we do this and then this. And the reason we write it like this is because, you know, E could be 0 or it could be really big, and it kind of depends on how many edges there are relative to the number of vertices. Whether we might be able to simplify this, but it's useful to write it that way to remind us. It kind of depends on how many vertices there are versus how many edges. We'll talk more about that, because that comes up a lot with graphs. All right, I think that's all we have time for. But again, this is being recorded, so I'm going to post a video pretty quickly on the website. You can go back and if you missed something. Also, I think I said this, but I'll remind you that I have a PDF of lecture notes that are available on the website. So like all of this stuff is all written in there. So if there was, again, if there were some details that you have more questions about, or it's helpful for you to look at it written down, you can look at that as well. Alrighty, have a good weekend. See you all on Monday.